This video is about the Euclidean algorithm, so this is not about the extended Euclidean algorithm, but the basic version of the algorithm. However, if you want to understand the extended Euclidean algorithm, this video is a good start. The Euclidean algorithm uses the GCD, so we first need to understand what that is. GCD stands for greatest common divisor. The GCD of two numbers a and b is the greatest number that divides both a and b. So if you would look for numbers that divide a, and for all numbers that divide b, then you can look at the divisors they have in common, and you can take the greatest. So let's do an example. We want to calculate the GCD of 12 and 60. So we start by listing all numbers that divide 12. Then we're going to list all numbers that divide 60. Now we're looking for numbers that are common divisors, so numbers that divide both 12 and 60. So those are numbers that appear in both lists. If we highlight them, we can see that those are 1, 2, 3, 4, 6 and 12. So those are the common divisors, but we're actually looking for the greatest common divisor. So that will be the greatest number that we've highlighted, which is 12. So the greatest common divisor of 12 and 60 equals 12. Let's do another example. We want to calculate the GCD of minus 35 and 45. So again we start by listing all numbers that divide minus 35. Those are 1, 5, 7 and 35. You could also put a minus sign in front of those divisors such that we get other divisors. Minus 1, minus 5, minus 7 and minus 35. However, we're looking for the greatest common divisor. And the positive divisors are always greater than the negative divisors, so we can just ignore the negative divisors. So now we're going to list all numbers that divide 45. And now we're going to look for common divisors, so numbers that divide both minus 35 and 45. So those are numbers that appear in both lists. So those are 1 and 5. Now we're looking for the greatest common divisor, so that will be 5. So the GCD of minus 35 and 45 equals 5. Now the GCD has some special properties to keep in mind. For example, it doesn't matter in what order you use the numbers. So the GCD of a and b equals the GCD of b and a. Another property is that you can put a minus sign in front of the numbers without any consequence. So the GCD of a and b equals the GCD of minus a and b. In fact, it also equals the GCD of a and minus b. It even equals the GCD of minus a and minus b. Another property is that the GCD of a and b equals the GCD of b and the remainder of a divided by b. If you don't understand this right away, don't worry, we're going to show examples later. And the fourth property is that if you take the GCD of any number and 0, the answer will be the absolute value of that number. So the GCD of a and 0 equals the absolute value of a. Now that we know what the GCD is, let's talk about the Euclidean algorithm. Calculating the GCD can be difficult if you use large numbers. So what we can do is simplify our GCD calculations using the properties 3 and 4 of the GCD that we just saw on the previous slide. So we can simplify our GCD calculations using properties 3 and 4. By using these properties, we're using the Euclidean algorithm. So how does it work? Well, let's calculate the GCD of 36 and 10. Of course, we could do it like we did it before. We list all divisors of 36 and all divisors of 10, and then we look for common divisors and we take the greatest, such that we find greatest common divisor to be 2. But we're not doing that, since we're using the Euclidean algorithm. And for that we're going to use the third property that we've seen before. So the GCD of a and b equals the GCD of b and the remainder of a divided by b. Since we're using 36 and 10, we're going to replace a and b with 36 and 10, such that we get that the GCD of 36 and 10 equals the GCD of 10 and the remainder of 36 divided by 10. Now if we're going to divide 36 by 10, you see that we get 3.6. However, we're not doing that since we're looking for a quotient and a remainder. To find the quotient, we're asking ourselves How many times does 10 fit into 36 entirely? Well, the answer is 3, because 3 times 10 equals 30, while 4 times 10 equals 40, which is greater than 36. And now for the remainder, we're looking at the part that's left. And we can calculate that with a minus the quotient times b. So 36 minus 3 times 10, which equals 36 minus 30, and that equals 6. There's also another way to calculate it, and that's using a mod b. So 36 mod 10 also equals 6. So we find a remainder of 6. Now we can replace the highlighted part in the equation with the remainder that we've just found, such that we get a GCD of 10 and 6. So now we found that the GCD of 36 and 10 equals the GCD of 10 and 6. So we can find the GCD of 10 and 6 to find the answer. But how do we do that? Well, we can use the same rule that we've used before. So remember that the GCD of A and B equals the GCD of B and the remainder of A divided by B. So we can put that into the equation such that we get that the GCD of 10 and 6 equals the GCD of 6 and the remainder of 10 divided by 6. Now if you divide 10 by 6, you'll see that you get a quotient of 1 and a remainder of 4. So we can put that remainder of 4 into the equation, such that we get a GCD of 6 and 4. Now to calculate the GCD of 6 and 4, we can use the same rule again, such that we get that the GCD of 6 and 4 equals the GCD of 4 and the remainder of 6 divided by 4. Now if you divide 6 by 4, you get a quotient of 1 and a remainder of 2. So we can put the remainder of 2 into the equation and then we get the GCD of 4 and 2. To calculate the GCD of 4 and 2, we're going to use the same rule again, such that we get that the GCD of 4 and 2 equals the GCD of 2 and the remainder of 4 divided by 2. Now if you divide 4 by 2, you see that 2 fits exactly 2 times into 4, so you get a quotient of 2 and no remainder, or a remainder of 0. So the GCD of 4 and 2 equals a GCD of 2 and 0. Now to calculate the GCD of 2 and 0, you might think that we're going to use the same rule as before, but we're not doing that, because b equals 0, so that would mean that we have to divide by 0. Instead, we're using another rule. We're using GCD of a and 0 equals the absolute value of a. That's the fourth property that we've seen before. So the GCD of 2 and 0 equals the absolute value of 2, or just 2. Now this is what we have, and we can clean up the redundant parts of this calculation, such that we get that the GCD of 36 and 10 equals 2. Now this is the Euclidean algorithm. There's also another way of writing it down, and that's by using a table. If you do that, then you create a table with 4 columns, A, B, and the quotient and the remainder of A divided by B. And now we're going to do exactly the same thing as we did before, but we just write it down in a different way. So we start again with 36 and 10, and then we're trying to calculate the GCD of 36 and 10. Now we did this before, and we found a quotient of 3 and a remainder of 6 when you divide 36 by 10. And then we use this rule that the GCD of A and B equals the GCD of B and the remainder of A divided by B. Now the fourth column of the table, that actually is the remainder of A divided by B. So we can just replace the highlighted part in the equation with the R from the table, such that we get that the GCD of A and B equals the GCD of B and R. Now if we look at B and R on this line, then we can actually use those as our A and B on the next line, such that we can calculate the GCD of 10 and 6 as we did before, and then we found a quotient of 1 and a remainder of 4. Now we can use our B and R from this line again as our A and B on the next line, such that we can calculate the GCD of 6 and 4. And for that we have to divide 6 by 4, and we did that before, and then we found a quotient of 1 and a remainder of 2. And now we can use the B and R from this line as our A and B on the next line, and then we can calculate the GCD of 4 and 2. and then you have to divide 4 by 2 for that, and you'll see that 2 fits exactly 2 times into 4, such that you get a quotient of 2 and a remainder of 0. And now we're going to use the b and r from this line again as our a and b on the next line. But at this point we can't use the same rule again, because b equals 0, and that would mean that we have to divide by 0. So instead we're going to use this rule. And for that we don't need a quotient and a remainder on the last row. So the GCD of a and 0 equals the absolute value of a, which means that the GCD of 2 and 0 equals the absolute value of 2, which is just 2. So the answer is actually on the last row of the table. But for this row we use the b and r from the previous row. So the answer is actually also on that row. So when you see that r reaches 0, then you know that the answer is on that row in the column of b. So the answer is actually the absolute value of b, where r reaches 0. And since the answer is already there, we can skip the last row of the table. So when r reaches 0, the answer is the absolute value of b from that same row. And by doing it this way with the table, we're also using the Euclidean algorithm. So we've seen 2 different notations for the Euclidean algorithm. They're almost exactly the same, but the right one is a table, and we're keeping track of the quotient and the remainder. So which one is better? Well, the table notation has some advantages over the regular notation. And that is that you don't have to write GCD with the parentheses over and over again. And because you're keeping track of the quotient and the remainder, you see what you're doing and it's easier to find mistakes. It's also more convenient for the extended Euclidean algorithm, because then you need to do something with the quotient, but we'll see that in the next video. Now let's do another example. We're going to calculate the GCD of 13 and 56, and we're starting with the table notation right away. So the first thing we do is create a table with 4 columns, A, B, Q and R. And we're going to use 13 and 56 for our A and B. Now we're going to calculate the quotient. So we're asking ourselves, how many times does 56 fit into 13? Well, that's of course 0 times, so the quotient is 0. We're going to use A mod B to calculate the remainder. So we're going to do 13 mod 56, and that will give us 13, so the remainder is 13. And now we're going to add another row to the table, and we're going to use the B and R from this row to the next row, such that we have an A of 56 and a B of 13. Now if you look at the A and B of the first 2 rows, you see that they have flipped. Why is that? Well, that's because we started with an A that was smaller than a B. And if we do that, the algorithm flips them. So actually it would have been better to start with an A that is greater than a B. So to calculate the GCD of 56 and 13 instead of the GCD of 13 and 56. Because then we could have skipped the first row. So let's continue with our calculation. How many times does 13 fit into 56? Well, that's 4 times, so we get a quotient of 4. Now if we do 4 times 13, we'll get 52. So the remainder is the difference between 56 and 52, which also equals 4. We could also have calculated the remainder using 56 mod 13, which also gives us 4. So let's add another row, and we're taking the B and R from this row to the next row. So now we're asking ourselves, how many times does 4 fit into 13? Well, that's 3 times, because if you do 3 times 4, you get 12. And 13 minus 12 equals 1, so that's the remainder. And you'll see that 1 fits exactly 4 times into 4, so we get a quotient of 4 and a remainder of 0. And now r equals 0, which means that the answer is in a column of B. So the GCD of 13 and 56 is the absolute value of 1, which is just 1. So the GCD of 13 and 56 equals 1. If you want to practice more examples, or if you don't want to practice at all, you can use the online calculator on the website. It works as follows. You enter 2 numbers, then you make sure that it's set to the Euclidean algorithm, and then you click calculate. And after that, the table will appear below, and the answer is highlighted. The link to this online calculator is in the description of the video. And let's give a summary of the table notation. you create a table with 4 columns, A, B, Q and R. Now on the first row of the table, A and B are just the A and B that you start with, and Q is the quotient of A divided by B, and R is the remainder of A divided by B, which can also be calculated with A mod B. Now on any other row of the table, A has the same value as the B from the previous row, and B has the value of R from the previous row, and Q and R are still the quotient and the remainder of A divided by B. When R reaches 0, you found the answer, because that is the absolute value of B on that row. So you create a table with the following properties, and when R reaches 0, you stop creating new rows, and then the answer of the calculation is the absolute value of B on the same row where R equals 0. Thank you very much for watching. Please have a look at the description for a link to the online calculator and for a link to the next video about the extended Euclidean algorithm. There's also a link in the description to a webpage that explains the same as this video, so that can be useful to have an overview of everything that's covered in this video. Thank you very much and bye bye.